Hello Year 5 and welcome to this week's science lesson, which is about understanding the splitting of an atom. So before we begin, can we just write the lesson objective and the date please, as well as the starter subheading. So just pause the presentation here and complete that before heading on. Right, our starter. So look at the information that you might have found from last week. What do you notice about the protons, electrons, and neutrons in each element's atom? Please write a sentence about what you've noticed. So these are some of the elements that you might have found out about last week. So the protons, electrons, and neutrons number. What do you find, or what can you notice about the amount of protons, electrons, and neutrons in most of the elements' atoms? Can you please, underneath your starter heading, begin your sentence with "I have noticed that," and then complete your sentence. So pause the presentation here and spend around 2 or 3 minutes writing that sentence. Right, what you might have noticed is that for most of the time, or the majority of the time, an element has the same number of protons, neutrons, and electrons in their atoms. These atoms are what we call stable atoms. A stable atom is when the forces within an atom are balanced. So the forces keeping the protons, neutrons, and electrons are the same because of the number of protons, neutrons, and electrons in the atoms are the same. Now, sometimes some atoms are called unstable atoms, and these atoms have an imbalanced number of protons and neutrons in their nucleus. Okay, so for unstable atoms, the atom itself is always trying to eject a proton or a neutron to balance out their atoms. So that means there is a lot of energy within these unstable atoms. Now, can you remember isotopes from the end of our previous lesson? Now, isotopes, if we can remember, here's our friend the element of chlorine. He's back again. Remember, the elements can have different versions of themselves called isotopes. Now, chlorine has 27 different isotopes, and that means its mass number represents a mean average of the mass across all of these isotopes. So 27 different mass numbers all added together and then divided by 27 gives this mass number for chlorine. Okay. Now, the isotopes are all the same element but have a different amount of protons and neutrons in their nucleus. Now, how do you think that could happen? Now, this is because some atoms can be unstable. So when an atom is unstable, it means the forces within the atom are imbalanced. That means that across some of these isotopes, some of the atoms of these isotopes are imbalanced because there is a different number of protons and neutrons in their nucleus. The number of protons and nucleus within these atoms aren't equal. They aren't the same. That means the atoms are unstable. Now, when it says the forces within the atom are imbalanced, it means that an atom by nature is always trying to become balanced. It's always trying to get all those numbers the same for the proton, neutrons, and electrons. So it's for an unstable atom, it's always trying to eject a proton or a neutron out of its nucleus. So and then it's stable. Now, for a quick challenge, can we please write the subheading "Quick Challenge" and try and match these terms with their different definitions in your book? So it just acts as a mini little recap of what we've learned so far because it's very important. So we have isotope, stable atom, and unstable atom, and we have the 3 definitions to the right-hand side. And as a mini little extension, you can think further. If an atom is unstable, what do you think that could mean for its energy levels? Would it have more energy or less energy? Write what you think below your definition. So can you spend around 5 to 10 minutes on this little quick challenge here? Okay, so pause the presentation here and spend around 5 to 10 minutes on this challenge, depending on when you're finished. And now here we have our quick challenge answers. So please get your purple pens out and make any changes that you might need to the definitions. And for the thinking further part, we've got an unstable atom has a lot of energy because the number of their protons, neutrons, and electrons are unbalanced. And remember, they're always trying to balance out. So they're always trying to eject these subatomic particles to balance out. So they're quite energetic. Now, nuclear fission. Okay, it sounds quite complicated, but don't worry, it's not too bad. Have you heard of a nuclear power plant? We know one famous cartoon character who works in one, but do we actually know what goes on inside a nuclear power plant? What is the main purpose of a nuclear power plant? Now, can you write what you think could happen within a nuclear power plant? So here's a clue. It has something to do with energy. So just below, can you pause the presentation here and spend about 2 or 3 minutes writing, I think a nuclear power plant is for, and then write what you think. Pause the presentation here and do that for me, please. Now, nuclear fission. So a nuclear power plant is where nuclear fission occurs, and I didn't expect you to include that in your answer. But what I might have expected to see is that nuclear power plants are involved in the production of power. Now, nuclear fission produces a lot of energy which is used for power, such as electricity. And this is what happens within nuclear power plants and nuclear reactors. Now, what is nuclear fission? Nuclear fission involves neutrons being fired at really high speeds at stable atoms. And this happens inside a nuclear reactor in a power plant, okay, as this diagram shows below. So I'll explain this in a second. So what happens is a neutron is fired at a stable atom, okay? This makes it unstable because then it has an unequal or an imbalanced amount of neutrons and protons in its atom, in the atom itself, in the nucleus, okay? Now this energy causing it to become unstable causes this unstable atom to then split into 2 different atoms. And in this process, it releases subatomic particles and creating a huge amount of energy. Now, this causes a chain reaction which continues across millions and millions of other unstable atoms, which in total produces a huge amount of energy. And this energy is then converted into power and electricity for us. Right, let's just go into a little bit more depth on nuclear fission so we can understand. So the neutron is fired at really high speeds towards this stable nucleus. And what this does, it means it becomes unstable because now it would have an unequal amount of protons and neutrons in its nucleus. So the neutron itself is absorbed by the stable atom and it makes it unstable then. Now this unstable atom tends to be an isotope of uranium called U-235, and these atoms are particularly unstable, which is great for nuclear reactors because we want as many of these reactions happening as possible so that more power is produced and more energy is produced and then more power is produced because we can get more electricity from the amount of energy that's produced. So what happens is this unstable atom has so much energy that it splits into 2 different atoms now, and this splitting releases two small atoms here, and it releases 3 neutrons. Now what this means is that this reaction can then happen again to further stable atoms. So this causes 3 more stable atoms to become unstable, and it causes a chain reaction. And this sort of reaction keeps happening and unfolding in the nuclear reactor, causing lots and lots of energy to be produced, and that means that lots more electricity can be produced. Okay, so it creates a huge amount of energy which can be used for power. So from this diagram shows a simplified version, but from 1 neutron, it continues, the reaction continues and creates a huge amount of further reactions from this 1 reaction. Now let's depict our own nuclear reaction, okay? So in our books, we're going to create our own nuclear reactions by cutting and sticking the neutrons atoms and arrows. Now, don't worry if you can't print off the cutting and sticking part, we can just draw it. That's no worries at all. Okay. So how many more can you draw in the chain reaction before you run out of room? So let's see as an example. Okay, we have our one neutron here, and it gets fired at our stable atom. This becomes unstable and creates two further atoms here, and splits into two further atoms here, and also releases 3 neutrons. Now these neutrons then get fired into these 3 atoms, which become unstable and split into 2 more atoms and fires out 3 more neutrons, and this happens for the other 2 as well. And remember, this reaction keeps going and going until lots and lots of energy have been produced. So in your books, can you either cut and stick these atoms, arrows and neutrons? But if you can't cut and stick, that's no worries at all. I want you to just draw this reaction here, okay? And I want to see how many more reactions can you fit on your page. It might be best to turn your page landscape for this task. And can you spend around 15 or 20 minutes on completing this task before carrying on? So pause the presentation here and complete this task. Now our plenary, okay? Let's have a think. So the chain reaction causes a huge amount of nuclear energy to be released. But how does this energy become power which we can use? Okay. Now this is a simplified diagram of what happens within a nuclear reactor. So using this diagram, can you spend around 5 minutes looking at this diagram and thinking how the energy released within this nuclear reactor from the nuclear fission can be turned into power that we use in our homes? Okay, so just to finish off the lesson, can you spend around 5 minutes looking at this diagram and come up with your own suggestion? After that, we're all finished, and I'm looking forward to seeing you next lesson. Okay, goodbye.